Hi everyone, myself Dr. S. Kannappan. I'm presenting the course Computer Architecture and Organization. Today we will discuss Module 2, the instructions and the instruction cycle. Module 1 we discuss about RTL, Register Transfer Language and micro operations. So we covered what is RTL, how the RTL micro operations are represented in Register Transfer Language, and what are all the different kinds of micro operations, and the architectural point of view to implement those micro operations also covered in module 1. Now we'll enter into from micro instruction level to a normal instruction level. How the instructions are executed by using instruction cycle. That also is covered in module 2. So just a review as we have discussed. So we introduced some registers and micro operations we discussed, and then we discussed some basic concept about memory and memories, different types of memories, and what is there in the CPU and cluster. Now we'll discuss about instruction design, mainly about instruction design, and then micro operation sequencing and role of different registers. So the most reference for this all the content is the textbook Computer Organization from by Maurice Mann. So computer instruction and overview. So if you see, the memory is having program. It contains instructions, and these instructions are fetched from the memory through data bus, and it will stored in the processor. And these instructions are executed by generating the control signals, and it will perform this operation. And also it will take the input and output based on the program we have coded. The input and output data it is transferring is in the ASCII code level. So the model of registers we have considered in this approach is these are all the following model registers, and register length is for the valid discussion it is considered, and it will be vary from processor to random. So the program counter we have considered is 12 bit, and address register 12 bit, instruction register 16 bit, data register 16 bit. So accumulator register and input buffer register and output buffer register, as it is taking in ASCII data, it is 8 bit, and sequence counter register just to count the clock cycle, and E some flip flop bits indicates the status of interrupt. So this in terms of register length it is represented. So the PC, the purpose of PC is to keep track of the next instruction to be executed. An address register just to store the address of the program in the memory. And data register just it will get the data from the memory, whatever the data. Sometimes the data may be instruction also. So that at that time the instruction will be transferred to IR register. When it is getting the instructions from the memory, that is also content of memory, but it is instruction. But while executing the instruction needs the data, so at that time also it will go to content memory, and it will access the content that will be stored in the TR. And AC is the accumulator register, just to for the temporary purpose. The results will be stored in AC. Intermediate results will be useful. That will be useful for the further process can be stored in AC. INR output input register and output register. The sequence counter is on the clock cycle. So these are some status flags E and R. So stored program, as we know, the stored program concept is the computer organization approach. So the program will be stored as a set of instructions and data in the binary language, and it will be stored in the memory, either it is in disk or RAM. So program can be executed only from the memory. As it is program is stored in memory. From memory, it will fetch the instructions and it will execute the process. So the process of execution is discussed with the help of instruction cycle. So what is first, before understanding the instruction cycle, first we should know about the instruction set. What are all the instructions that a processor can execute, and what is the format of the instruction that the processor is designed with the particular set of instructions. So this is the instruction format, or we can say instruction architecture. So instructions consist of three fields: operation code and address or data next, the mode bit. The mode bit or opcode bit. Opcode bit is there. The mode bit is as a part of opcode, or it's separately indicated as opcode. So mostly it is some mode bit and then opcode and then address or data. So next we will discuss this one. So the hierarchy, as we said, instruction hierarchy, it is based on the number of bits allocated for the opcode. So opcode bit is 4-bit, means it can perform to 4 instructions, and the remaining is used to specify the address of the data, or address of the memory. If it is 12-bit is allocated here, the instruction 16-bit out of 16-bit instruction, 12-bit is allocated for address. The address may be memory address, or it may be sometimes the data also. And the opcode bits are 4-bit opcode, 12, 13, 12, 13, 14. 12, 13, 14, only 3-bit output. 8 instructions it can perform on mode bit. So if it is 3-bit output, so 8 instructions, 2 to 8 instructions are possible. Depends on the mode bit, it may change, and instructions can be so same instruction can be accessed in different ways. So here 3-bit opcode instructions sometimes supports 0 to 6 instructions. 1 bit is 7th bit is indicated for toggling operation. So 7 instructions out of 7 instructions are used, and 1 is for toggle operations. And the mode bit indicates either direct addressing mode or indirect addressing. So this is the classification and what are all the available instructions in the MANOS instruction set. So the instruction is divided into 2 parts actually. The opcode 0 0 0 0 0 0 1 1 1 0 6 bit of 6 up sorry, up to 6 0 to 6 7 opcodes. In the 7 opcodes, these are all the instructions. When it is 0 0 0 and operation, 0 0 1 add operation, 0 1 0 load accumulator, 0 1 1 store accumulator, 1 0 0 branch unconditional BUN, branch save at BSA, when it is 1 1 0 ISJ. And if it is 1 1 1, if opcode is 1 1 1, last one, it is registered reference instructions. It's completely register reference instruction. The register reference instruction, these are all the instructions. Clear accumulator, clear E flag, complement accumulator, complement E flag, circular right shift, circular left shift, increment, uh, shift if positive, shift arithmetic if positive, shift arithmetic if negative, shift arithmetic if zero. Okay. So this kind of shift operations and halt and so these are all the register reference instruction. And when IO reference instructions can also be used, that depends on the direct bit or mode bit. When it is mode bit is 0, we'll use all the register reference. When mode bit is 1, we'll use all input output instructions. Some instructions are used to access directly the input devices and output devices. This is input output, skip on interrupt, skip on input, skip on output. Interrupt or interrupt off, ION, IO off. But whereas for of course 0 to 6, it is completely about logical as well as some and arithmetic operations. Except logical operations, arithmetic operations are there mostly. Some are logical operations. It is a combination of logical and arithmetic. And when direct mode bit is 0, it will perform uh, some operations. If mode bit is 0, it will perform some other operation. That depends on the mode of accessing the memory. So whether it is direct mode or indirect mode. If the memory specified is direct address, then it is direct addressing mode. If the memory specified some indirect address, means it is under indirect addressing. This based on the 3 fields, so we can classify different types of instruction. So there is an important issue with applications. So there are 2 types of applications, right? Application specific and general purpose application. So computers find complex instruction set, or it may be reduced instruction set. Some applications, some embedded applications, they may require some simple instructions instead of complex instructions. But if you use for performing complex algorithms using this system, it needs more number of instructions to be coded. The program will be costly. Then better to use this system. For complex algorithms, it's better for simple algorithms, and risk is better. And instruction processing and pipelining. So instruction cycles means how the instructions are executed in a sequence of micro operations. So it has 3 parts: fetching and decoding and execution. So that can be organized. So the pipeline stages can be organized. So fetching the data from the memory, calculating the address for the data, and before fetching the data in the execution part. So it is also can be separated in one separate stage. Let us discuss that instructions contains. As we have discussed previously also, so there is an instruction sequence counter. So the sequence counter will be used for counting the clock cycles, and it will be a reference for the executing the instructions. For performing decoding, it needs some clock cycles. For execution, it needs some clock cycles. For address generation, it needs some clock cycles. So based on the clock cycles counter, it will give, then only it will take appropriate steps while executing. So these are all some kind of timing signals: T0, T1, T2, T3 to Tx. So there is a decoder. The decoder will create some states. So when the count is 0, 0, 0, so it will be in this T0 state. When count is 1, it should be in T1 state. When count is 2, it should be in T2 state. So it will be already based on the availability of the resources in the processor. It will be decide the number of states to execute the program, and the corresponding decoder and sequence counter will be used for achieving this. So first one is fetching. Fetching instruction means getting the instruction from the memory into the processor. So the memory, the instruction address generally will be stored in the program counter. The program counter value has to be sent to the memory. From the memory, it has to be given. So, but here, when the processor wants to interact with the memory, it needs two registers. So one is address register and data register. So first, the address register must hold the address of the data from where the data is accessed. Okay? So the program counter, it is having in the processor register, and is having inside the processor. This program counter value address will be stored into AR register, that is in the T0 clock cycle. And next, in the next cycle, what it will do, so some AR, the PC to AR, so the AR will be transferred to M of AR, memory address. So now this is from memory, it will transfer the data to the DR register, and it will create the data register. When it will load, when the PC is available, it will be load. So next, it will be the data from the data register is loaded into instruction register. So every register, when we are loading destination register, when any register is used as a destination register, we need some load instruction. So this is controlled from the control, some other control circuit, it will control it. Right. So steps T0, just it will store the PC to AR. From here, it will send to memory of address, and it will perform that process pointing out will be performed in T1 state. In T2 state, it will get the data. So the data will be transferred to instruction register. So, and it will be divided it into the three parts: mode bit and opcode bit and address bit. And so based on the decoding, in T4 cycle it will decode, and T5 cycle it will go for execution. So right, so how it will decode means it will be connected to the opcode bits are connected to a decoder. Decode logic will be connected to a control logic here. So that enable the particular device based on the controls, increment, clear, and all those things it will perform. So next we'll see the programming concept. So we know this programming concept: assembly level language, high level language, and machine level language. So all kind of languages we use to program. Some kind of instructions we are using in the assembly language. Mostly we are using assembly level language and register transfer language. Both we can generally we use interchangeably, but the assembly level language is easy to interpret. So instruction categories we have discussed, like register reference instruction, memory reference instruction, and IO reference. So that we'll discuss one by one. So register reference instructions, right here we have a general purpose register, it is accumulator register, and a flip-flop register. So we perform operations on these two registers only. So when it is 0002 0002 110, it will perform all the memory reference instructions. When it is 111, it will perform register reference instruction or IO reference instruction. So when it is 0, then it is instruction register reference instruction. So all the operations, mostly if you see register reference instructions, either it will perform operations on accumulator, or it will perform operations on E flag register, what we can say, the status of the some kind of operation. Very simple, just binary code. We have mentioned this support for this one based on the binary code of the instruction. When it is zero first bit is zero, then only it is register reference, and the output is 111. Yeah. So next remaining all bits are 12 bits are 12 bit register. So 12 bit address. So this is coded from 1000 0100000100. So every time we are keeping one bit as one, remaining bit as zero. So the one flying from MS bit to LSB bit. So based on the code, it will perform some operation. So this is nothing but some. If you see, this is in hexadecimal 0 to 1 is 7, 1 double 0 triple 0 is 8, remaining 0. So when you do right shift, this 12 bits, one bit will be used for the next position. It will be flow to the next position. So these are all some operations. Clear accumulator. Clear accumulator means accumulator register will become 0. Clear E flag. So clear E flag means the carry flag, like almost carry flag will use. E flag will be cleared. Complement accumulator. Accumulator will be complemented. 0 0 0 means 1 1 1 8. 0 becomes 1, 1 becomes 0. Complement E, so flag bit, only one bit, maybe 0 or 1, but you will complement as per the current status. And shift right we have discussed circular shift, and increment also we discussed previously. And these four these instructions are used for some kind of branching instructions. Skip if positive accumulator. So that means accumulator is positive means it will skip the next instruction. Skip if the accumulator is positive. Skip if negative accumulator. So if the accumulator value is negative, just it will skip and go for the next instruction. Immediate instruction will be skip. As it is, as you said, ASC specified. So mostly the specific reference instructions are performed on and so halt is nothing but control. Halt is one more instruction which is not completely about register transfer, register related, but it is related to register reference, register related data particularly, because when you stop the program, it will be the temporary values will be stored in the registers. Halt value, halt the program. You see one by one. So clear complex, simple AC becomes 0. Clear complex is from 1 becomes 0, 0 becomes 1. Very simple. Simple instructions. So, but the circular right instruction is represented like this. So, right instruction, rightmost bit, A of 15 will be this E flag. The LSB bit will be stored into the E, and E will be rotated to A of 15. So first, so E is stored in A of 15. Okay, this A of 15 is stored in is equal to E, and E is transferred to origin. So this is nothing but circular shift operation. Similarly, opposite direction also is also possible. The A of 0 is stored in the E, and E is transferred to the AC of 15. It is left shift operation. Left shift means this the leftmost bit will be changed. The leftmost bit will be changed with the carry. The remaining instructions are like skipping the next instruction. Skipping means it will be incremented by one more time, so that it will skip fetching the instruction from the previous PC. So now, register reference halting the instruction, last one actually. So it disable all the circuits. So now let's see the memory reference instruction one by one instruction. This is a little bit some complicated instructions are also available in this. So memory reference instructions. See, So when the opcode bit is 0002 110, is classified into memory reference instruction. For each code, one instruction is allocated in two modes. Again, the mode bit is 0, which indicates the direct addressing mode, and mode bit is 1, it indicates indirect addressing. But the instruction is same, the mode of accessing the operand in the memory is just that differs. So in the direct addressing mode, the storage at the specified instruction register address. So that is the memory address specified in this memory address field. So the instruction is AND, for example, AND instruction if you take I is equal to 0 means opcode is 000. An instruction address, whatever the address it is specified in this instruction, it is called instruction address. This address will indicate the address of the data. So if it is indirect address mode, if I is equal to 1 for the same 00 AND operation, it will perform the address AND operation with the data present in the address of this memory, and again that address will be considered as the address of the address location is present here. Previously just this is the address, but here in indirect address of the actual address is specified here. First transfer to DR data stored in the specified IR. That is, it will go to first address, and that address, the data stored in the address will be transferred to DR. Again, then after transferring DR to AR, access this fetch status. Now this DR value is transferred to again address from AR. It will again go to the memory location and get the actual data. That is indirect addressing. So let's see this RTL representation of all these instructions. So when it is direct addressing mode, so I is equal to 0 is indirect addressing mode, direct addressing mode, and mnemonic and 000 is it is not I is equal to 0, and mnemonic it is nothing but 4 opcode. Opcode is 0 and it indicates and the memory of AR. So memory of AR means the address register. The address register is loaded with the address specified in the address field. This field data is loaded into AR, and M of AR means the content available in the that particular address pointed by AR is loaded into DR. Now, so the DR data, that is memory data, is AND with accumulator. So accumulator is AND with data available in memory. Similarly, add operation. Add means again same. It will get the data from the address specified in the instruction and it will store in the DR. That DR is added with the accumulator and the result is stored in the accumulator. Next, load accumulator. Load accumulator is load the accumulator from the memory. So from the memory address specified in the instruction, and M of AR is transferred to DR. So DR is equal to accumulator. It will be transferred to accumulator. Now store accumulator. So next one is store accumulator. Store accumulator is it will store the data available in the processor into the memory. The data is available in accumulator. From accumulator, it will transfer the data to the memory. So to store the data into the memory, first the address register is required. So the address is specified in the instruction. The accumulated data is stored into the data register. From data register, it will send to the memory. It is nothing but a write operation. Load accumulator is nothing but a read operation. Now branch unconditional. Branch unconditional is so where PC is executing some instruction and suddenly it wants to transfer to some other instruction. So at that time So branch unconditional is changing the address of the next instruction. So unconditionally branching to the new instruction. So that is branch unconditional. When PC is executed, PC address is zero address. So zeroth instruction is executing means suddenly after executing the zeroth instruction, you don't want to go to the first instruction, you go to some other instruction. So that address has to be stored into the PC. New address has to be stored into. So that is, so the address specified in the instruction register is stored into first AR. Now the AR has to be so the branch annotation. So AR of 0 to 11 is address specified. That address specified is stored in AR, and now AR will be transferred to PC. Branch annotation. So this is branch BSA instruction. BSA is branch, save, address, and increment. So this is the, it will store the written address. That's the thing. So IR of 0 to 11 is instruction specified, the address specified in the instruction register will be transferred to AR. From AR, it will be the PC value, the current PC value. The next instruction to be executed, the PC value will be sent to the M of AR. It will store that, save the address. So that is a backup, temporarily storing the PC value. Now PC, new PC is nothing but this next address to the AR. So AR first one, increment, branch, save, address, increment. So this, that is nothing but. So it will transfer the current address to the memory, and it will increment the current address to one more time, and it will be taking that as a new address. So next one is ISZ. ISZ is nothing but increment skip if 0. Increment skip if 0. This indicates AR is equal to, so IR of 0 to 11. First address will be stored in the specified address will be stored in the AR, and the value present in that memory will be read to the DR. That DR value is loaded into accumulator. Now accumulator is incremented. So if incremented value will be checked for whether it is 0 or not. So that's how it will check this. So it will store that value into DR, and from DR it will go to memory, and it will check if this value is equal to 0 or not. If it is 0, then it will skip the next instruction. Simply accumulator is incremented, and then it will skip the next instruction to be. So skipping the next instruction to be executed is nothing but incrementing the PC value. PC is readily finding the next instruction. So if it skip and it will go to the next instruction, it will increment the PC by one time. Similarly, now memory references. Indirect. So in that indirect addressing mode, so one more step needs to be performed. So the step needs to be performed is the address specified in the instruction. The address specified in the instruction has to be loaded into the AR. From AR, it will go to the memory. From memory, it will get the data present in the memory into DR. Now, DR value is again loaded into AR. From now, again from AR, it will go to memory. That content will be loaded into DR. Okay, so this two steps it has to go. This is a common step that every instruction needs to perform, apart from the logic it will do. So for suppose this instruction I and instruction, when I is equal to 1 and the mnemonic is 8, so that is opcode is 8. So and operation it has to perform accumulate with DR. What is DR actually? Previously DR is only this one, first one only. So M of DR is equal to transfer to DR. But it is one more time it has to do this one. So DR value will be transferred to AR. Again from AR it will be M of AR will be transferred to DR and add instruction. Similarly, accumulator has to be added with DR. So, but DR will be accessed twice. So, how we are getting DR means we have to go to M of AR. AR is nothing but address specified in the instruction, and it will get the data. Again, we have to repeat the same cycle. So, this DR will be transferred to now new AR. You go to that new AR and memory location, and from there you get the DR. These two instructions will be in this. So it is going from one more step it has to perform. So similarly, load store instructions clearly mentioned here. So first, the here address value will go to memory, and get the data into the DR, and it will be stored into the. So that is nothing but direct addressing. When it is indirect addressing mode, it will do twice. It will do two steps. Two times it will go. First here will be transferred, and from here it will go to DR. So DR will be transferred to again here. From here it will go to memory to DR, and it will perform AND operation or logical AND operation or addition operation, and it will store the result in accumulator. So now, branching is an instruction that explicitly modify the PC during the execution branch. So the simplest the next instruction to be executed is not located in the next continuous mode of storage. So like while do operations. If it satisfies, then it will go to the next instruction. That is loop continuous. Not it will be terminated and it will has to go back to some other instruction. So that's why it is skipping this one. So the next instruction it is M is storing this one. This is this one, it is in busy. But the next instruction is not this instruction, it has to go to some other instruction. So now this address has to be loaded into this branch. So with respect to the class like this, can indicate this one. So in T0, just it will go to PC will be loaded into TR. So sequence counter is incremented by 1. So just to indicate TR. Next T1, M of AR is stored into instruction register. It will get the instruction into IR, and PC is incremented. So because it is readily available for fetching the next instruction, first instruction fetching is over. Next instruction. So first step is just calculating the address. Next step is fetching. Fetching, it is readily pointing the next address. And now the sequence counter is 1. Now T2 is it will perform decoding. After decoding in T3 class cycle, it will get the data and fetching the data from the memory. Now T4 class cycle, it will perform the operation. After T4 class cycle, it makes its execution is over. When execution is over, sequence the counter becomes 0 again. So this fresh it will start with the new cycle. Again, SC will be incremented if it calculates the new instruction address. But in the execution part, so this indirect addressing mode. In indirect addressing mode, DR will be stored into again DR. The DR will be stored again in DR. It will not perform this execution. Instead of fetching this during execution, it will one more step. It will in T4 it will get the DR. Again it will go and get the new DR will be loaded into AR first. From AR, again it will go to memory and get the DR. So one more class cycle it is T4. In T4 it will execute in the direct addressing. Indirect addressing mode, it needs 2 more class cycles. Calculate the address in one cycle. In next cycle, it will transfer the data into the DR. And in third cycle, in the T6 class cycle, it will perform and operation. Now, unconditional branch instruction. So, like as we have discussed, unconditional branch instruction, PC is changed unconditionally. So, if I is equal to 0 and I is equal to 1, when I is equal to 0, direct addressing. So, the address is transferred to PC simply. The new address is specified in the instruction. That address is transferred to PC. Now, the process will go to the PC address and it will get the instruction into the data. But if it is an indirect addressing mode, so first it will go to memory. AR2 AR will be loaded into M of, if you go to M of AR, you get the data here. Again, the data is indicating this action. This address will be stored into PC. Directly address will not be stored. This is stored in a memory location. In that memory location, the data will be fetched. That data is the new address is loaded into PC. This PC value is taken as a reference and it will execute the. So now branch cell return increment. So subroutine call will be there at this point. So the PC is the next instruction. So the PC value will be do the address. The AR00 is nothing but the new branch instruction where it has to go to this place. So before going to this place, it will store the PC into memory location. PC will be stored at this point. Subroutine call. Before going to the subroutine call, the next instruction, the PC will be loaded into the M of AR. Here, generally it will indicate the next address. Some other address also can be specified. Then it will store the AR. Now, PC is nothing but new subroutine address will be available in the, because in subroutine call it will indicate the where it has to go, the PC. So PC will be loaded into M of AR. That M of AR is go to subroutine instruction. Then now PC is incremented and it will be continued. And the skip will be 0 instruction. So very simple, just it will increment the accumulated. And if it is accumulated with 0, then it will increment the PC. So this is very simple. Current instruction, this branch instruction. So PC will be stored with this branch instruction. This branch instruction is nothing but skip to 0. So this has to go to some other instruction. And the accumulated value will be stored in the data. It will increment the data value by one time. If it is 0, then it will continue the instruction. If not 0, then it will go to the branch instruction. It's just it will skip the actual PC and it will go to the branch instruction. Then 0 or greater than 0. The next one is input output instructions. In the input output instructions, the output is 1 1 1 1 1 2 1. So when it is 1 1 1, it is either it is register transfer or IO transfer. So when already we have seen the register transfer. Now see the IO transfer. For IO transfer, mode bit is equal to 1. So here, the polling, the interrupt concept will be there. Instruction to support programmed polling. Polling refers to waiting for a condition to be true before proceeding. So it has to wait until the generally when an interrupt occurs, then only it will go to some other program and it will execute. Interrupt program, it will go to interrupt program and then execute. If it is interrupt is not occur, then it will not execute that interrupt. Here it's nothing but a program. programmed polling concept. So instead of interrupt, just it will wait for a program for a condition to be true. So it will wait some condition to be true. Condition is true, then it will go to the some program return. So it is some polling is nothing but some kind of language process. Because of waiting time will be more. So instead of waiting, just it can do some other program, and if an interrupt occurs, then only it will check its priority. The priority is high, then it will go and execute. So during meanwhile, it can execute its own program. Now, if you see the input output instructions, there are four instructions. Ask input instruction. INP means input instruction. So this input instruction, it inputs the ASCII character from the keyboard to the processor. So to receive that ASCII character, it has to give the instruction as input instruction. Next, out instruction, output ASCII character. So the ASCII character has to be sent by the processor to the display device or some other output device. The skip if input flag. If the input flag is equal to 1, just it will skip the next instruction. Skip SCO, skip if the output flag is equal to 1. So here it is input and output instruction. Okay? How it will perform? When input is wants to be transferred ASCII character to the some processor. From keyboard to processor, it wants to send the data means it will send peripheral interface between input device, input output device, and then. So here it is. See, there is a printer, keyboard, and printer. So the processor is processor. So it has a transmitter interface because the keyboard is a device. You can see transmitter interface. But the printer is at the output side. Maybe receiver interface or output. So in the input interface, the INPR register will be there, and similarly at the output interface, out register will be there. Okay? So for the data transferred from the keyboard will be stored into the INPR data. From INPR register, it will store it into the register. What I can say, this is a small accumulator register. That accumulator register will hold the data coming from the keyboard. And if it is printing, means this, it will send the output data output register to the printer, but the data coming to the output register thing, again the data available in the process. The accumulator register is having the data. Accumulator register value is loaded into some output register, some like a buffer register, and it will be sent to the printer. At the same time, it indicates so two flags. Flag indicate buffer, indicating buffer empty. So buffer empty, buffer full. So if this one, it indicates full. 0 means it indicates nil. It's empty. Yeah. So if the data is available in the INPR, so keyboard is received the data, received the data from the keyboard. Then FJ status is equal to 0. So once the data is placed in the buffer, it will keep on until it is loaded. Yes, release it. Next, output register. First, initially it is output register. If this buffer is not full, it will transfer FGO 0, and it will show FGO 1 once the transfer is finished. Next we'll go to interrupt and we'll discuss, and we'll go to instruction cycle next. So instruction and interrupt both will be included here. You can check the instruction cycle will happen or interrupt cycle. So both cycles can be handled in one approach. So let's check the interrupt first, and then we'll go for the instruction. Because instructions, we know it will do fetching, decoding, and execution. But interrupts, how it will execute is depends on the interrupt enable. So if interrupt enable is equal to 1, it indicates interrupt on. If interrupt enable is 0, it indicates the interrupt off. So if interrupt enable is equal to 1, then it will indicate some interrupt has to be processed. So it will make FCA 1, FCA 1, and 1 means it's completed, and it will go to R is equal to 1. So R is equal to 1 means it will go to the instruction cycle. It will go there and it will do instructions. So otherwise, if it is 0, then it will check the output flag. Is 1 means again it will set the instruction cycle. And it will. So that is nothing but R is a flip flop set for IO device state. Device for IO device state. So if R is equal to 1 means interrupt cycle, R is equal to 0 means instruction cycle. R is equal to 1 means it will go and take the data from the input device, or it will send the data to the output device. 0 means it is an instruction cycle. So instruction cycle means it will do fetching operation and the decoding operation, execution and so on. So let's assume that R is equal to 0 and it is in the fetch cycle. So it is in the instruction cycle. The instruction cycle, it will fetch the instructions from the memory. So it may be readily available with the memory to fetch the instruction. From PC it will go and fetch the instruction, but another flow we discussed. And it will be executed. Before execution, it will do calculation of the data address and getting the data into the memory, into the processor, and then it will perform that particular. The execution is completed, then it will check for the R value. Every execution of instruction, every time when an instruction is executed, it will check whether R is equal to 1 or 2. Like it is flag to indicate whether it is in interrupt cycle or instruction. So if it is interrupt cycle, assume if it is interrupt cycle, then it stores the return address in location 0, and so PC value is storing this into the temporary address 0th memory location. Because when it goes to interrupt cycle, while executing the interrupt, it has to check all the register values. So register values has to be changed. So that may cause the loss of the intermediate results in the main program. That's why it will store the return address in a particular program, and it will go to the main memory and PC interrupt program. There it will do. It will reset all the IAM and R equal to 0. So because R equal to 0 means it is in the interrupt cycle. So there it will go and perform the interrupt for a particular. So this is an interrupt handling, before interrupt and after interrupt concepts. So before interrupt, say if PC is in 256, current instruction is 255, and next instruction is 256. Simply it will PC will be loaded into AR, and AR it will go to store the data, to perform the operation. But if it is with interrupt means, if it is with interrupt, so we want to consider with interrupt means someone will store the return address in zeroth location. Then it stores the return address in zeroth location. So, like so PC will be loaded into a temporary address M of 0. Okay? So here it is stored, and the branch to the location 1 PC will be loaded into uh, new program where it has to go and execute. So for suppose at 0 it is 256. Okay? So the next instruction will be stored. The 256 is stored in the M of 0. And PC location branch to 1, PC is equal to 1, where this branch unconditional. In this instruction, branch unconditional. So where this branch unconditional means it will go, PC will be loaded into 1120. So it will be go to this IO program. In IO program, it will execute the IO program, and finally to return this one, branch unconditional to 0. Okay? So it will go to branch unconditional to 0. In 0, what is the address it is, what it is doing? It is getting this data from this one, and it has to load it into PC. Now it will go to 256. That is the return address, return instruction address. So likewise, it will execute the interrupt handling. Control logic to calculate the different kinds of states, T0, T1, T2. It will calculate the states by using some counter and additional decoding logic. So this decoder will generate the particular state that control will generate either it is T0, T1, T2, T3. So finally, timing and control is the main important point, important topic where it will decide the this exact flow. The cycle will be performed as it is or not, where in which clock cycle it has to perform which task will be decided by this control logic. So in the next session we'll discuss about the different kinds of control logic. There are two types of control logic: hardwired control logic and microprogrammed control. Mostly will so far whatever the control logic we discussed, that is hardwired control logic. So to improve the efficiency, we'll go for a microprogram. What kind of advantages there with microprogram? Thank you. So there are some quizzes are available. Just take the quizzes and cross-check the answers. In the answers, we provided the explanation for each and every quiz question. If anything is required to discuss, we can discuss, post the questions in the particular link we provided. So this is available in my personal website link, so you can access the remaining courses also available in the and lecture notes also provided for this each and every module. So you can go through the lecture notes, and this PPT also it is uploaded. You can store this PPT and you can access the PPT also. So for every module, we plan it into one PPT, and it has some video explanation for the PPT and lecture notes for the preparation. So both are aligned to the module, particular module. Thank you. See you.